Hey, welcome back to the Rust tutorial series where we learn to be proper Rust agents and develop in Rust. Today we're going to talk about an extremely important feature of Rust, which is ownership. And ownership is in part what makes Rust Rust, so it's a very idiomatic feature. In order to explain to you how ownership works and why we need it in the first place, I need to explain to you the way a computer manages memory. And for this, we have two memory management models, which are the stack and the heap. Let us first look at the stack because it is somewhat simpler. In our main function, we create a variable a, which is a 32-bit signed integer. This variable is stored on the stack. The stack is divided into a part of the memory that is currently being used and a part that is still free. In order to separate those two parts, we have a stack pointer that points exactly at the place where the free and the used memory meet. So if we create a second variable called b now, which is 64 bits in size, the stack pointer will travel 64 bits down and the variable will be stored directly after a. This also works in the same way if you have a function called foo here that has local variables. In this case they are called c and d and are 32-bit floating point variables. Again, we create c and d in order on the stack and we move our stack pointer by 64 bits in total. Once we finish with the function foo, we can see the interesting way that the stack works. Because the variables c and d were only local to the function foo, and therefore they are not needed outside, we can delete them, so to say. But instead of deleting them, whatever this would mean, we would just move the stack pointer back by 64 bits. So we're again after b, and this denotes that c and d, even though they are still in memory, are not part of the stack anymore. So we can reuse that memory. And in fact, if we create another variable, here called e, the space that c was taking is just reused. So this seems like a really easy and efficient way to use memory. You always know where to store new variables, which is just after your stack pointer, and you also know exactly how to delete them, which is you just go back with your stack pointer until you have finished the scope in which those were needed. So this seems like a very easy and also efficient way to manage memory. Number one, we always know where to store new variables, which is just after the stack pointer. And number two, we know exactly how to get rid of them, which is just moving the stack pointer backwards. However, let's examine a non-trivial example. In this case, we don't have a variable that has a known size as we knew before. But now we have a dynamic struct, whatever that would be. You can think of it maybe as a string, but it doesn't really matter. So in this case, let's say s is being constructed and it has a certain size. After that, we maybe create a few other variables. Those are pushed onto the stack, no big deal. However, now we want to expand s. Maybe think of it as adding a few characters to a string. Suddenly, this string is a bit longer, takes a bit more memory, and we really have a problem now, because s wants to take more space in the stack, but it can't, because it is constricted on both sides by other variables. Now you could say, well, no big deal. Let's just push those variables that are on top of the stack a bit outside, and we can then make space for s. However, this is a really bad way to deal with dynamically sized variables, because this would be slow and inefficient. Just think of a stack that is full of variables, and every few function calls you dynamically resize some of those variables that are on the very bottom. Every time you do this, all the other variables that are on top of this resized variable would need to be shifted around, and this is slow and very inefficient. Entering the heap. This is our second memory management model that we typically have in a computer. So compared to the stack, you see that the heap is a very fragmented space. It's not as clean, it's not as organized. In here we have a few chunks of memory that are already taken. Could be by your operating system, by your browser, or by other variables in your program. The heap always works in conjunction with the stack. So if we create this dynamic struct on the heap now, the following thing happens. At first, we create a pointer on the stack. And this can easily be done because this pointer always has a fixed size. For example, if you have a 64-bit operating system, a pointer will always contain 64-bit because it stores the address of where the actual data is in your heap. The next thing that happens is that your computer will look for a space in the heap that is sufficiently large to house the data you want to store in your dynamic struct. For example, it could choose this gap to store your data. And now we see that we have a pointer on the stack that points to the address in the heap where the actual data is stored. So if you want to access your data, you would just need to follow your pointer into this heap address, and there you can find your data. If we now want to resize that data and need just a little more space, we could either be lucky and the gap in the memory is large enough, or as shown in this case, the gap might not be large enough and therefore we need to move this data. However, because this is not the stack but it's the heap, we only need to find a new position for the actual data that we're storing, and we don't need to shift all the data around. You see the stack pointer just follows, and the old memory is now freed again. Now what is interesting, and what is kind of the core of the problem that we want to discuss today with ownership, is what happens if this variable goes out of scope. So in this case we have a quite easy setup. The first thing we need to do is we need to free the heap space, because of course we still require the pointer to find the data in the first place. And the second thing we need to do is decrement our stack pointer so that now s, which is the pointer on the stack, goes out of scope. Now, however, imagine what happens if we would have 2 or 3 references or pointers to the same data structure. Who will handle the freeing of the data on the heap when it goes out of scope? This is exactly the problem that ownership solves, and we're going to see that later on in the video. But first, let us wrap up our small comparison between the stack and the heap. The stack is a nicely organized data structure that has no gaps in it. Therefore, it can operate very efficiently and quick, but its downside is it only works for data with a known constant size. As soon as we have a data that is dynamic in size, we need to go to the heap. The heap is a large, fragmented space where allocation and freeing is quite expensive, because we always need to look for those gaps instead of knowing exactly where to store it. However, the advantage is the heap can handle large and especially dynamically sized data. Let us now check out how variables on the stack, on the heap, and how ownership works in Rust. At first, let us create a very simple example to see how the stack works. As we said, variables on the stack have their size defined at compile time. So if I say I want a 32-bit integer a and equal that to 8, it gets stored directly on the stack. We then have a second variable b, which is a copy of a, also 32 bits. And then we want to print both of them. So we just print line a equals, and then we put a in here, b equals b. And let us just run this. We see, as expected, a equals 8 and b also equals 8. So on the stack, we just make a copy of whatever is there. We also saw that as soon as a variable goes out of scope on the stack, it just gets deleted. So let's just create an empty scope here, and we create a variable c, which could also be an i32, and it's equal to 15. We can in here, of course, print c. So let's say c is equal to c. And this will run, of course, no surprise. But if we now try to print this variable outside of its scope, we can see that Rust will give us an error. The error is cannot find value C in the scope. This is to be expected because at this point C goes out of scope. And it is no longer valid to use C afterwards. So let's just comment this out because we know it won't work. In a second step, we now want to explore how variables on the heap are dealt with. Unfortunately, we didn't have contact with any variables that we could create on the heap until now. If you remember, we only had variables I, U, and F, which would be signed, unsigned, and floating point numbers. And all of those had the size directly engraved in their names, so they definitely have a constant size. In order to give you an understanding of what the heap does, we have to introduce a new variable type, and in this case I chose to use string. So there is two types of strings that you can have in Rust. The first one are string literals. So let's create another scope in here. Let's say we have a string called name, and this is going to be Rust. So the way string literals work is they are denoted by the ampersand and then str in lowercase, and those strings are compiled into your binary file, which means they are part of the program, and as such you cannot change them. So if we were to say let's make this mutable and just add some text, name plus equals rocks, this is not going to compile. Again, we can run this code and look at the error message. And Rust tells us we cannot use the plus equals sign on type str, and this is because string literals are immutable. They are part of your binary, and as such they are constrained in their memory space, and they cannot be expanded. So let us just comment the whole thing out because we know it doesn't work. If we want to have a mutable string, we need to use the string class. So the string class is denoted with the uppercase string. And in order to create a string, we can, for example, use the string from method and include a string literal here, for example, Rust again. This will create a string for us from a string literal, with the from method being in the string namespace. Don't worry, we're going to talk about namespaces later on, but this is how you create a string. Or it's one way to create a string. Of course, we then need to make this mutable in order to be able to change it. And now we can say name plus equals rocks, and this will finally work. Then we might use the string. For example, we could just print this. And we see this works. Now let us try this again outside of the scope and run it. And you will see that again, we cannot find the variable name in the scope, meaning that in terms of going out of scope, a variable on the heap behaves exactly like a variable on the stack. And what is especially interesting here is that not only the pointer to this variable that is on the stack goes out of scope, but also the variable itself, so the data structure that is on the heap, gets cleared up. And this is not something that you can expect from every programming language. For example, if you compare it to C++, let's say you would make a new variable here on the heap, then your pointer to this variable would go out of scope. But you would have to manually call delete here in order to tell C++ that the data part of the variable that is actually on the heap can be deleted. If you don't do this, you will have a memory leak, and over time your memory will run full and you can no longer allocate new variables. Other languages deal with this problem by introducing a garbage collector. For example, Java, JavaScript, and Python do this. They have a system that is constantly running in the background and that is checking whether some variables that are stored on the heap do no longer have a pointer from the stack pointing to them. If that is the case, they will just delete this memory. The downside of this is that it can be quite unpredictable when this garbage collector will run, and that in case it does run, it will always cost you a lot of performance. So for languages that are actually performance critical, like C, C++, and also Rust, it is preferred to have manual memory management, which means memory management by the user instead of memory management by the garbage collector. However, there is a very different approach between Rust and C++. In C++, you as a developer have to manually call the delete, while in Rust you need to clearly define ownership. So now let's finally get to what this ownership is. Ownership in Rust means that every value has exactly one unique owner. In this case, we know that the data structure, Rust, that is somewhere on the heap, has the owner with the variable name, name. Once this unique owner goes out of scope, the data on the heap is going to be deleted forever. Now, if we were not able to transfer ownership, we would have no way of getting this variable out of the scope, right? However, we do have a way to transfer ownership. Let us create a second variable that is in the outer scope. We'll call it target name, and we're not going to initialize it for now. However, inside the scope, we are going to transfer ownership from name to target name. We just do this with the assignment operator equals, and this means from here on out, the data that was formerly stored in name has now a new owner, which is target name. So here we transfer ownership. Let us look at a graphical example of what is happening here in the memory. We have a string which is called Rust, and we assigned it to a variable that I called name1 here. Of course, we have this pointer on the stack that points to the value Rust somewhere in the heap memory. Then we create a second variable called name2, and we transfer ownership from name1 to name2. In this moment, a second pointer is created on the stack, and at the same time, the old pointer name1 is invalidated, and Rust now knows that name1 is no longer valid, which means you can no longer use it, because name2 is now the owner of the data Rust and can do to that data whatever it wants to. If you're familiar with C++, this would be something that would be called a move operation. Now, outside of the scope, we can now use target name because it is defined in the outer scope, and you will see that this runs perfectly. However, because we've now transferred ownership, at this point we can no longer use name after ownership has been transferred, because name now no longer is the owner of this data Rust and therefore can no longer use it. So let us just run this, and we will get a very expressive error message from Rust here. We can see that the value moved here, meaning that the value of name moved into target name, and afterwards we cannot use name anymore. And what Rust also tells us is that a move occurs because name has the type string, and the string does not implement the copy trait. Now don't worry about what traits are. It just means in this case that a string cannot be trivially copied. If you, for example, look at the 32-bit integer, it does have the copy trait. Here in line 3, a copy happens, because both A and B are on the stack, and values that are on the stack just get copied. However, here we have only the pointers that are on the stack, but the actual data is on the heap, and therefore we transfer ownership instead of making a copy. Now we could circumvent this by using this clone function that the compiler suggests, which means that explicitly you want to make a copy of this data structure. However, if we do it like this, we transfer ownership and name can no longer be used. Of course, with only having a unique owner and one way of transferring ownership, we would still be very, very limited in what we could do in Rust. Just imagine the scenario where you need 2 pointers to have access to the same data value. You couldn't do this with transferring ownership because only one variable can own the data. For this, we have borrowing, which we're going to go into in the next video. I hope this explanation was very clear and that you now understand what ownership in Rust is, and that ownership works very different on the stack versus on the heap. This is a core concept of programming efficient and safe Rust, so you always need to be aware of whether you're having a value on the stack versus when you have a value on the heap. If you could take anything away from this video and learn something, consider giving it a thumbs up and subscribing. In the next video, we're going to go into borrowship, which is the second very idiomatic concept that Rust has for memory management. Until then, stay comfy.